Hi, folks. So we are looking to talk about an end-to-end concept of DNA data storage system here. I'm Shruti Sethi from Microsoft and also worked quite a bit with DNA Data Alliance, which is one of the groups under SNIA that works towards DNA data storage system. And I'll let my colleague also introduce himself. Olivier, if you want to go ahead.
Olivier, I'm the system CTO for Biomemory, and I'll explain how we are implementing the standards and where we are in terms of the DNA data storage appliances.
So today we will look at it by also referring to an interoperability spec that is being built in the DNA Alliance system, which is essentially for the end-to-end data storage concept. So let's quickly go over the agenda first. The first section you will see is basically the abstract concept of the DNA storage end-to-end system. We look at interoperability standards, some logical interfaces that are needed between the subblocks of DNA storage, the kind of system operations that this system would have to support, and also the type of DNA data storage racks that could be considered. All of this is essentially referring to the interoperability specification work going on. And based on this, we will also look at a real system implementation, which Biomemory is leading, and which will also look at what were the strategic enablers there, how is the integration in the data center, what is the performance and the current status over there. So let's start from the left over here, which is essentially the lab view of where DNA data storage has been tested repeatedly, which is essentially storing the data and being able to retrieve and check for errors and quality. From there, we are looking to transition to the right side, which is the way we know, which is the rack kind of equipment that we know on the DNA, on the data centers. While we make this transition, there are a couple of factors that have been of importance that the DNA Alliance is also working for. Of course, the read-write costs, but also scalability, speed, reliability of the data that is actually stored and retrieved, and the interoperability, which also implies that it should be integrated with the automation as we scale and put them in data centers. With these factors, the interoperability spec also calls out the use case scenarios. And for starters, it actually looks at a span of the archival use cases. So on the left side, you will see archival use cases with high retrieval speeds. On the right end, you see what is called the extremely cold archive. Think of like the backup scenario, or essentially backup used in case of maybe disaster management. And the idea is that starting with the use cases on the extreme right, the technology would be able to move more and more towards the left and maybe beyond this as the technology advances. Okay. So this is the first block view of the end-to-end storage system. The 5 blocks you are seeing on your right hand that are boxed together, those are the core internal subblocks of the DNA storage. These include the encoder to encode the data, but also then the synthesizer, which is essentially the writer. The storage and retrieval, which is basically holding the DNA content once it's written. The sequencer, think of that as the reader for the DNA storage. And lastly, the decoder, which brings back the data in the original format. I will refer to all of this as DDSS in some of the slides going ahead. Along with that, you also see an orchestrator block shown over here. We'll double click into this block in just a minute, but this is essentially, this is the concept of the main brain of the end-to-end system. So it is basically channelizing all the transactions and keeping a visibility of everything. Before we double click into that, one more thing shown down below over here are the extra resources that might be needed for the system's functioning. This, of course, includes the regular power IT, But since it is a DNA storage, this also includes some liquid plumbing and waste handling, since there are reagents involved in order to synthesize the DNA and read the DNA. My colleague here will also show how this liquid plumbing and waste management might be simplified in some of the implementations. Let's talk a little bit more about that brain or the orchestrator over here. So the concept of the orchestrator is essentially something that has complete visibility into all the transactions going from the user to the actual DNA storage. Not only that it has visibility into all transactions, it also logs the current status and any kind of errors from the subblocks of the DNA storage system. So that helps the orchestrator in decision-making of alarms, any kind of major errors, any kind of retry signals, which essentially means the orchestrator is able to see when any part of the entire pipeline has faltered or has an error more than expected and there needs to be a correction. One other thing that the orchestrator is able to do is basically monitor the entire system level error. So this concept is also touched upon in the spec, essentially because the net error that is seen in the system might be coming from different sub-blocks, might be an accumulation of different sub-blocks. So the orchestrator is the only one who has visibility into the error coming from all of these sub-blocks, such that it can configure some of the sub-blocks to provide coverage. When I say coverage, think of it like coverage to combat the extra error. So it is the only one that is able to have the entire accumulated system error view. Okay. Now we'll talk about how is the system going to function. So think of 3 phases of functioning for the system. The first one is the system assembly. That is basically before the system exists at all. We are integrating the system or putting together the sub-blocks. The spec calls out a couple of attributes that need to be matched or checked. For example, the encoder and the decoder should be compatible in a number of attributes. The synthesizer, which is the write, and the sequencer, which is the read, should again be compatible in some of the attributes. The sequencer might need to be aware of the amount of error that is introduced during the synthesizer storage steps, so that during retrieval and sequencing, enough coverage can be provided to combat that error. So all of these attributes might need to be checked during the assembly phase. Then we come to the setup or initialization. This is essentially the phase where you are configuring all the information that these subblocks need to know before they start functioning. As an example, the attributes that are to be sent to the encoder and decoder, and which depends upon what is the encoding algorithm used. These need to be written in before the functioning starts. So that all of those steps are covered in the setup phase or initialization phase. And finally, when the system is done, it can go to the step 3, which is the functional phase, where it can actually handle all the transactions. The next thing that the specification talks about after the phases of operation are the logical interfaces between sub-blocks. So here as an example, we'll only talk about the logical interfaces for synthesizer, but essentially the spec talks about these interfaces for each of the sub-blocks. The synthesizer, which is the writer, is basically getting the entire transaction, which might include some metadata addressing the actual user's data that has to be stored. But it also might receive an extra signal, which is the retry. If you remember, we mentioned retry when we spoke about the orchestrator. This is the orchestrator directly telling the synthesizer, rewrite what was sent to you before. And it might be a decision made based on the visibility that the orchestrator has to the errors that are occurring in all the steps. Now consider the synthesizer received these inputs. It does not get a retry signal, but it's getting a new transaction packet. These are the kind of outputs that the synthesizer might need to give out. The first one, of course, the most obvious, the synthesizer is the one that converts the digital to the DNA strands. So the DNA strands that then transition to the storage step, that is the first output. But along with that, there might be a number of feedback and error signal that it needs to provide. For example, the current cycle status, whether the cycle is in progress or done. There might be error flags for, say, if the error rate was seen higher than the specification or expected rate. There might be error flags for, say, if the reagent levels are extremely low in order to complete the current or the next cycle, warning the orchestrator for a refill before the next cycle comes in, or warning for a maintenance. So there are these number of other feedback signals that the orchestrator will get to collect from the synthesizer step. Okay. As an example, we only looked at the interfaces of the synthesizer, but of course, in the spec, you can refer to the interfaces of other blocks. We'll now transition to talk a little bit about two more things. The first one being the kind of operations handled. So this end-to-end system, of course, it has the regular read and write operations that we need to handle. But when we come to an erase or delete operation, for a DNA storage, the erase could be thought of at two different granularity levels. So we spoke about writing the content into DNA strands. So we now have DNA material. This is stored in the containers, storage containers. If my erase has to be implemented at the granularity of a storage container level, that essentially means safely flushing out the DNA content. But if the system decides to implement a lower than storage container granularity of erase, keep in mind that this would mean reading the existing content in the container, writing back only the content that is to be saved, and then flushing out all the old content of that container. So it might be a multi-step over here because of the special way that DNA storage works. Again, modify would be a combination of different steps, reading the current information, modifying and writing it into a new container, flushing out the contents of the older container. There is one last operation that we talk about in the spec, which is an optional, which is essentially a self-check that the system could do during its idle time. This means writing a known golden data file or data set and basically reading it and checking for errors just to maintain the overall system performance and visibility into it. Lastly, in the spec, we discuss the kind of racks that could be imagined for this system. We talk about it in three different types. The first one being a traditional single rack, where we are saying that all the sub-blocks of the DNA storage system are actually housed into one rack such that one rack can independently operate. And in case of scaling, that entire rack is multiplied. But there could be other variations where we say n racks act as a single set. That essentially means now it is these n racks that have all the 5 essential components doing the DNA storage work. So in case of scaling, this entire set of n racks is going to be scaled. Or I could go to the other extreme and say that it could be a disaggregated rack system. Now essentially I have X number of non-identical racks. Maybe some racks are supporting writes, some are supporting reads, some are supporting storage. And in case of scaling, I might want to scale only 1 or 2 of these type of racks. If I want more writers in the system, that is the only type of rack that I scale. If I just want more storage space, that is the type of rack that I scale. That could be an other end of the implementation that is an extremely disaggregated system. From here, let me hand it over to my colleague here from Biomemory. He's going to run you through a real example of actually implementing the system.
Okay. Thank you, Shruti, for the introduction. I'll explain a little bit what we are doing and where we are in terms of the system implementation. Biomemory is part of the SNIA DNA Data Storage Alliance. And we are still a small company, but we are basically aiming at contributing more and more into this domain. So Biomemory aims at developing appliances, data storage appliances, to be deployed in data centers. okay? And I'll walk through what is our plan for that and where we are. But obviously, when we want to do that, and I think there have been many presentations before during the conference about it, we need to talk about something that is obviously cost-effective, reliable, and operable. So, I mean, everything has been built that way in order to comply with the data center environment. The way it works, as Shruti explained, is that we are assembling DNA blocks that are representing binary information. So in our case, we use blocks that are engineered to represent 4 bits, quarters, and we have 16 of those to be able to map to the binary stream. The key thing is that when you engineer those blocks, you want to engineer them so they are easily readable. That's the key string. Because when you read, you use sequencers, life science type of sequencers, like Shruti explained. And in the life science, you have billions of combination of things that you want to detect, like when you do genome decoding or something like that. But in our case, we don't care about that. We want this very simple. We want a strong signal to be readable for a limited number of type of blocks, 16 in our case, but we could do more or less. So that's basically what is the key heart of the technology from Biomemory, is to be able to read those blocks and have only 16 blocks, which is very simple. Those blocks are consumables. And so this is something that in the system we have to manage. This is like a printing kind of operation. We store things in containers. In our case, we have chosen to store things into a credit card format because this gives us access to all the ecosystem, low cost and very robust ecosystem of the ATM banking industry and so on. And so this is basically to have a very low-cost environment. All the things from our strategy has been to be low capex, okay? And this is one of the things that I'll share with you on that, okay? So those are the elements, and we have been building architecture that I will show that for rackable system. So basically, all the blocks and functions that Shruti described, we have cut that in pieces so it matches the rackable and OCP format. Okay? So Biomemory, in order to enable that, have been working on 2 fronts. One is the biotech front, and the other is the system level front. So from a biotech standpoint, as explained, we have those consumable DNA blocks, and one of the challenges has been to produce that at very, very low cost. Most of the industry, the life science industry, is using oligo-based kind of chemistry to produce and synthesize DNA. We are not doing that. We are what we call biosourced. Basically, we replicate those engineered blocks that I was talking about with bacteria. And this is not done in data center, obviously. This is done offline. And we mass produce things for almost nothing. So that's a key enabler for this technology because it's a super low-cost production of consumable. And we have developed a system that on those 16 blocks that I was talking about, we can assemble that very fast, okay? In the parallel reaction, the assembly is a chemical reaction. We have a densification of that as well as speed of reaction. So all of this has been basically settled into the Biomemory biotech labs process. And today, the end-to-end, we are achieving very low error rate, and the blocks have been engineered that way. Whether that's for write or read, I mean, we achieve 90%. As we are densifying the reaction, I'll go through that. We may face a different error rate. We'll have to adapt probably, but so far, so good. I mean, we are above 90%. And the way the error correction code is working, we are more robust. Kind of 80% is what we can tolerate so far. On the system level, we have been building a totally modular structure because the functions in the system will evolve or are evolving at a different pace. So we build the architecture that way so that it can be rackable, we can change the rack. And the way it has been built is that what we call the biomaster, which is the orchestrator that Shruti was talking about, is something that is controlling everything, and the rest is very simple. It's more kind of embedded industrial kind of implementation. We have been focusing on industrialization and picking blocks and technologies from the industry that are available, low cost, and robust. Okay, and we are adapting that to the system. So the goal is for the CapEx to be very low. Okay, we have been obviously aligning with the and contributing to the SNIA digital DNA Data Storage Alliance, and all of this is made possible because the Biomemory biotech team is adapting the biotech aspect to the system. And that's something that is critical because when I'm telling the biotech team, hey guys, I mean, no, you need to respect this kind of temperature or this kind of thing or whatever, because that would be much cheaper and simpler and more robust into a data center environment, then they are capable of engineering that to match the requirement. So how does it integrate into a data center? Basically, you have two parts. You have the orchestrator and the interface and so on, which is basically a server that is exposing a S3 interface with a safe backend. And we use JBOD for, I would say, managing all the buffering aspect. And all the DNA-centric domain and blocks are basically hidden from the external world. So it's really seen as an object storage system independently of the fact that this is DNA. Obviously, there are some specific characteristics. The other thing that we have been building around is a dedicated channel for the control plane. I mean, the OEM, I mean, all the operation and maintenance. And here we are leveraging redfish and swordfish techniques. And basically, we intend to contribute to that and define the extension that are required in order to manage all those parameters. So that's basically how things are integrating, and we will upgrade the different writer and reader function as time goes over time. So if you look at the system, today 80% of all the components, hardware and fluidics and so on, are just reuse and adaptation of the industry available system. Like, I mean, for example, when we do printing of droplets, I mean, this is using printing techniques, the robotics for manipulating the DNA card storage is basically a credit card kind of robotics. I mean, the server, the top of the rack is obviously just a standard server, and the JBOD that we are including that. So all of this is existing, and we have to hack, let's say, the firmware and some of the software, obviously, to adapt to our technologies, but no R&D development from a hardware perspective. It's very, very low development. Most of the effort is software and firmware to adapt to that. And on the biotech, everything is ready, if you prefer. I mean, those blocks are being engineered. We know what knobs we can turn, and there are still development, especially, and I don't have time to develop that, but for the handling the metadata. This is a whole field of innovation around that. But basically, the rest is, in terms of writing and reading, it's available. So obviously, there are still a lot to do, okay, and it's a long journey. It's just at the infancy of this technology. So today, we are in the execution of, for next year, to release the first machine that we will use internally as the write as a service or DNA storage as a service. And we will do that until we feel comfortable that everything is bulletproof and we can release the appliance into a data center. So we are progressing in parallel in the write performance and in the read performance, and as well as the media storage capability. Everything is using existing technologies, okay? I mean, we don't have to develop things, we have to adapt things. So today, and I'll show where we are, the first stage that we're implementing is corresponding to a certain demand on the market. It's still fairly slow. We are talking about 2 gigabytes per day of writing. As we are densifying that, we will be able to move progressively, and I'll explain how, up to a very dense parallelization of all those assembly reactions that will allow us to do up to 100 billion in parallel and continuous way, which will basically be more than a petabyte per day of writing. And that's basically our goal for 2030. But today it's still very slow compared to this aspect. From a read standpoint, basically this is not what Biomemory is doing in terms of equipment. We are leveraging what is existing into the industry for sequencing. So today's sequencers, we use basically commercially available sequencers, and that's basically giving you a 2 megabit per second kind of range. And we can accelerate that with our software because it's block-based, but more or less that's the range that we're having. There are new technologies that are emerging, like solid-state nanopores or this kind of technologies that will allow us to go to a much faster read speed. So we are not worried about the read speed. We are more worried the focus on durability of those equipment. The current sequencers in the industry are not super robust, so we are working with the people to, assess how far we can push that and see select the right partners and technologies for that. But I mean, it's not a problem that we foresee to achieve 100 gigabit per second. Read throughput. The challenge is more slowing down the reading, and the challenge today is the signal processing and all the detection of signal. But as I explained, as we have strong signal by engineering our blocks, this for us is much easier and faster. From a container standpoint, we use credit card, we put holes in that, we call that wells, we deposit the DNA in that. So by using standard industry techniques, like PCB kind of hole making techniques, we can have fairly easily up to 1 million of those wells into the DNA, I would say, container. Okay, so where are we today? Okay, because it's a nice story and so on, but as I said, we're at the initial stage. So we are working in different axes of optimization. One is the miniaturization of the reaction, because this is driving how dense or parallelized you can make it for a given space, a rack, let's say. So that's basically today, for your information, when we started, we were starting at 10 microliter kind of range of reaction. Now we just validated a few weeks ago 1 nanoliter. Validating means we can write it, amplify it, copy it as much as we can, or we want, and then reading it back and turning that back into a binary string. So that's basically something that we have been validating for 1 nanoliter, which corresponds to 1 million sites. So, and in our case, we have currently 64 bytes per site, and so that's basically 64 megabytes per batch. Okay, and we are migrating to about 50 picoliter for 10 million sites before for next year. It's not really a problem. I mean, printers today, inkjet printers are basically picoliter range printing. So this is what we are leveraging. Obviously, it needs characterization. We are working also on the reaction acceleration in parallel. And that's basically something that today we're fairly slow. It's 1.3 days to write a batch. And but we know what to do in order to have about 3 batches per day next year. So that's basically, and we'll update the industry on that as we are progressing. In terms of system integration and automation, basically all the writing path has been designed, and we're in the implementation phase right now. On the reader, we have different options, as I said, in the sequencers from the industry, and basically we're in the assessment right now. Okay, what is the best strategy? Those are small equipments. I mean, sequencer today, just the sequencing part of it is the size of a USB key. So we can pack, I mean, and have a redundancy, massive redundancy if we need to, into the system, into a rack-able system. And the compute aspect is done on a server level. This allowed us to shape strategy and a roadmap in terms of use case. So today, we already sell and produce DNA for very small amount of data for things like tagging and anti-counterfeiting and identification and this kind of thing, NFTs. So that's basically the kind of activity we do today. Next year, we'll be able to have an official commercial offer for the write as a service and the DNA storage as a service, but still for quite limited amount of data. And we are talking about the notary amount or something like that. We are talking about gigabyte kind of range to be stored. As we are automating and miniaturizing and parallelizing all of this, we will be able to do archive with larger contents. So that, and we already have demand for that, like for banks and insurances and so on, we are talking about terabyte of data. And finally, once we will have the solid-state nanopore in industry well established, then we will be able to trigger more active archiving kind of use case. And obviously, will not have the capability of interact with, let's say, an AI engine or something like that, because, I mean, the latency and the random access will always be a limited factor, but that will be able to read it sequentially at a fairly high speed. So this is opening the door for quite a lot of use cases and in this domain. So that's basically where we are and where we are going. If you have any question for myself or Shruti, feel free.
Yeah, I have one. So you talked about the 90% error. Are you doing two things? Are you doing a read after write?
So today for the verification, the question is, are we doing, I guess, for verification, the read after write? Okay. So today, this is what we do. Okay, so we have a specific channel where we take the samples that we have been writing. As when we write millions of copies of those. So we take a part of that and we verify it, we read it. That's not our long-term strategy. I mean, there are other techniques that in the biotech world that can allow us to verify without having to reread. So that's what we are heading toward, but today this is, we have to read into a separate sequencing machine.
So that kind of feeds into the question I wanted to ask, was what is the overhead you think for error correction?
Okay, so the overhead is today.
Additional weight.
Today, because the engineering of the blocks is fairly robust so far, the overhead is about 10%, okay, in terms of the overall. And but what we don't know, to be honest, is as we reduce the volume of those reactions to picoliter, I mean, will it stay that way, or will it have to have a different way? This is the kind of thing that we have to do by next year, and we'll have the answer after, but I don't have the answer yet.
I have two questions. One is, you comment on the container part, how you use data from the container. Secondly, I'm curious about whether this kind of technology dependent on the sensor, because there's a lot of so for generation,
Yeah.
this kind of car dependent on that.
Okay, so the first question is how do we read from a DNA container? And the second question is are we sequencer agnostic or not? The first question is that when you have a container like that with wells and they are capped and sealed, so we unseal, so the DNA is dehydrated inside those wells. So to read it, you unseal the well that you decide to read. Today, our strategy is that we put 1 gigabyte per well. It's something that may evolve over time. It's flexibility because the density is so high in the DNA. We open that, we rehydrate, okay, and then we pump the content of the well. We redispense back what we don't need, okay, because it's easier to control. And then we feed that into the input of a sequencer, okay. There is a so-called preparation stage that we mix with some primer and this kind of thing. And while we transfer this liquid to the input of the sequencer, we do this preparation, and then we inject that into the sequencer and it's reading, okay. So this is how it works. For the sequencer level, basically, the sequencing machine is reading the DNA as it goes through membranes of pores or this kind of thing. And we have a lot of reading at the same time, very fast. And then there is a signal processing effort to extract the useful signal and then call it pattern recognition to detect whether that's block number 1 or block number 3 or whatever, okay? So we are sequencer agnostic, but we have to put a software layer on top. So we could use today, we use standard, for example, Oxford nanopore sequencers with their firmware, the low-level software. So, and once we get the base detection, then we have our own decoder, that's a biomemory software that convert that into a binary stream, okay? What we want is to have what we call a block caller, which is basically not reading base by base, but block by block, because we don't need more in our case. I mean, we have only 16 blocks and just read that. So that's basically the software is, or call it software firmware, is what we have to put on that. Otherwise, we are sequencer independent.
The
you're talking about the temperatures where we can. Okay. So, yeah. So the question is, how is the code resistant to environmental temperature once it's stored? So it's DNA, dehydrated DNA, when it's protected from humidity and UV light, is super stable. I mean, people in forensic are recovering DNA, reading DNA 20 years after on crime scene or something like that, and it's at the outdoor. So it's very robust. We can basically, so not as robust as ceramic, obviously, but in the data center environment, I mean, this is something that is not a problem. I mean, 60 degree, 0 to 60, it's not really a problem. So,
what is the temperature range, though? I know that it's very vulnerable to humidity.
Yeah.
Ambient temperature.
So, okay. So, sorry. So, what is the temperature range? Okay, so in the DNA Data Storage Alliance, there have been some work about defining how to measure all of this and the lifetime and this kind of thing. Because the way it works is that you degrade things slowly and more or less rapidly, depending on the type of environmental aggression, like water or humidity or temperature or something like that. But basically, for us, I mean, we're warranting 150 years over the range of temperature storage for the data center environment. So that's the kind of thing that we have reliability testing for that, and we exceed far this kind of limit, but this is what we think is we should warranty. Okay. How far can we push it from a temperature standpoint? This is something that we're still testing, especially in the space environment. We have requests for space, I mean, to have that in space, and that's basically one of the questions.
If I could add one thing.
Sure. No, that's.
I mean, what is, I mean, you're testing now, what is your aim? I mean, by 2035, you want to be where?
Well, I mean, and this is something that we have not finalized internally, but I'm coming from a semiconductor environment, so I think the specification from the semiconductor in terms of storage temperature is something that would be good. So that we are talking typically about 150 degree storage maximum.
I wanted to quickly add, so the DNA Alliance has one work going on towards endurance, which is basically endurance and how long the DNA material can last. And essentially it calls out that every container supplier, type of container supplier, whether it's more like a plate or a credit card or test tube, every container supplier provide an endurance testing along with it, that based on that kind of container, maybe the container has some kind of cooling, it doesn't have cooling, it's sealed, not sealed, based on that kind of container, what is the impact of humidity and temperature, and how that testing should be done and how it should be reported. So it has a specification coming out for the container owners who can, basically go through that endurance testing and then report.
But yeah, but the important thing is, and this is part of the whole purpose of the alliance, is that we'll be consistent as a standard
Right.
for all.
Yes.
So once you get that spec, it's the same kind of spec that all the suppliers
Should be following.
Yeah.
Hopefully.
So where can people find out and find this spec when it comes out? How can they participate?
So
Repeat the question.
The question is, where do we find the spec?
So I will quickly point folks to the bottom part over here. This is where folks can reach out in order to participate. This is not the direct link to these specs that we refer to, But this is the way to participate, and you'll be added to, if your company is a member of the DNA Alliance, you'll also be added, to the working groups. And as the specs are released, everybody who is the member will certainly be, and SNIA will be posting the specs.
How does DNA storage compare with other emerging technologies like glass, about possibility right bandwidth, and other secondary concerns, benefits?
Yeah, I think it's quite complementary for. Oh, sorry. The question is, how do we compare to glass, basically, right? Or to this kind of technology, or Terabyte or Microsoft Silica. So I think it's complementary. The DNA is much denser, and so that's one attribute. The equipment, so far, from what we see, the capex will be much lower, okay? And in terms of the read and write, especially on the read on the DNA, you have to pay the price because it's chemical system. You have to pay latency to access the first bit. Probably that even if we are working on reducing that, it will not be as fast as, for example, a terabyte system or something like that. So there are different trade-offs for different use cases, depending on the usage. There is an overlap, obviously. Cost-wise, it has the potential to be cheaper. As the consumable are cheap and the capex is cheap, it should be much, much cheaper than other systems. But there are some limitations, obviously, that we'll have to cope with.
Glass already has media fully,
Well, well, the media is always free. For whatever technology that beyond tape, the media will be. It's like those credit card, glass. The media stored once it's written, it's not the issue in terms of TCO. And that's a condition for it to be successful, whether that's ceramic or DNA. So the question is not that. The question is there is a capex question and an opex question, and there are different trade-offs that will be matching the different requirements in the industry. At least that's my view.
This.
Okay, I'm not sure. So the question is, what about read endurance? I'm not sure. So the way we read today with current sequencer, it's a destructive read. Okay, so basically you read and you destroy the DNA through the process. There are new technologies that are not destructive, but today this is. So when you do that, let's say we don't care, sort of, because we have so many copies of the DNA. So that's the first point. The second point, which is very important, is that there is a great thing about DNA. There is one attribute. There are weaknesses, but this is the key strength. The replication of petabyte is super fast and super easy. The copy is error-free, and we do that with what we call a biosource techniques. So that basically bacteria, and they know very well how to copy without error. So that's the kind of thing.
That was kind of the question.
Well, so that's the kind of thing that obviously when you copy, you can always introduce a small error. So if we copy and copy and copy, but we have, all the techniques. So we encode binaries, okay, into DNA. So all the digital techniques for error correction, for erasure coding and this kind of thing, all of this is at our disposal, okay, that we can translate that into the DNA space. Exactly.
And just to the last question, these kind of things would be some of the trade-offs that exist between, because DNA might have these kind of limitations but has other advantages, and they are also at different points of development, extent of development right now to sort of exactly compare.
Yeah, I think we are out of time, but thank you for your attention.
Thank you.